Homework 28, we are going to do a lot of finding solutions either for an interval or continuously when we have an equation. This one says find all the solutions of the equation in the interval between 0 and 2 pi. Notice we're including the 0, but we're not including 2 pi. 0 and 2 pi are really the same place on your circle, right? And so what we want to do is solve our equation for sine, cosine, tangent, whatever it may be, and then we're going to use our handy-dandy table that we've used a whole lot of times and look up where's the cosine equal to that value between our 0 and our 360. So if I go back here, first one here says cosine of theta minus 1 equals negative 1. To solve it, I'm just going to add 1. So I'm looking for where is the cosine of theta equal to 0, because negative 1 plus 1 is 0. So now I'm going to look back at my other sheet. So if I look down my list at cosine, where is it equal to 0? I see it's equal to 0 at pi over 2. And also at 3 pi over 2. Now normally cosine, sine, secant, and cosecant have a period of 2 pi. And so normally I'm going to have that, since cosine is positive in 2 quadrants, 2 different answers for my answers, which is what I have there. And so that's all I'm going to do. Pi over 2, 3 pi over 2, and I'm just going to have those 2 solutions then. Number 2, if I solve this one, sine of x plus 1 equals 0, I'd have to subtract my 1. So I'm looking for where's the sine of x equals negative 1. So again, I'm going to go back and look at my table. And so looking at my sine, where is my sine equal to negative 1? There's only one spot that I see that my sine is equal to negative 1, which is at 3 pi over 2. So that's going to be my only answer, 3 pi over 2. Now I believe sometimes on your note sheets I use the one with the circle where the cosine was the first value and the sine was the second value. So if you have that one handy, that one also works. Probably just as easy to use the big table and look them up because that has sine, cosine, tangent, and all of them. These first ones are only going to have sine and cosine, so when I originally did the note sheets, I used the circle one that just had sine and cosine, but this one probably is just as easy to use because we're going to use it on a whole bunch of them anyway. Going back over here to problem number 3, I've got to solve that one for sine, so first of all I'm going to add my 1. 2 sine of theta equals 1, dividing by my 2, sine of theta equals 1/2. So again, I'm just going to pull out my sheet and look on my sheet for where my sine is equal to 1/2. Pi over 6 and 5 pi over 6 would be my 2 values. And so that's all I'm going to do with that one. Solve my equation for sine or cosine and then look up in my tables which angles that would correspond to. Again, this is going to be in radian measures, so make sure you're using the radians, not the degrees, when you put your answer in. 4, 5, and 6, we're doing the same thing, solving for tangent, cotangent, secant, or cosecant. That's why earlier on those previous 3 I said this is probably just an easy table to use because then I don't have to have a different table. This one has all of my trigonometric values in there between 0 and 360. So this one's probably easier to use if you look at your note sheets. So again, we're just basically doing the same thing. We're going to solve our equation. So in this one I'm going to subtract my 1. We're looking for where the tangent of theta is equal to negative 1. So if I go back and I look at my paper, where is the tangent equal to negative 1? Looking down my tangent list, I have 3 pi over 4 and 7 pi over 4. So 3 pi over 4 and 7 pi over 4 are going to be my answers for where is tangent of theta equal to -1. On the next one, we want to solve that one for cotangent. First thing we're going to do is add 1. So we have the square root of 3 cotangent of x equals 1. We're then going to divide by the square root of 3. And of course we would want to rationalize that. So we're going to multiply by the square root of 3. We get square root of 3 over square root of 9, which we know is square root of 3 over 3. So we're looking for where is our cotangent of x equal to square root of 3 over 3. Again, if I flip back at my table, looking under my cotangent column, which is the last one, I need a positive square root of 3 over 3, so I have 4 pi over 3. Did I miss one? Yes, I did. Pi over 3. Pi over 3 and 4 pi over 3. And so those are going to be my two solutions. My board doesn't want to move the right way. Number 6, we're doing secant. So on this one, we're going to add our square root of 2. Once our board decides that it wants to be cleared off, add our square root of 2 and say that the secant of theta equals positive square root of 2. So again, I'm going to flip back to my table, looking under my secant column, second to the last one, I've got pi over 4, and I've got 7 pi over 4. So at pi over 4 and 7 pi over 4 is where the secant of theta is equal to the square root of 2. Easy as that, just looking those up on the table. Seven, 8, and 9 are solving basic trigonometric equations using your calculator. These are going to be in radians. I know that because it says between 0 and 2 pi. So I want to make sure my calculator is in radian mode. If you have one of the Casio calculators, you're going to hit the mode button twice. So you're going to hit mode, mode. You should see degree, radian, and gradient up on the top. We're going to hit number 2 so that we are in radian mode. So up on your calculator, you should see a little R up there to tell me my calculator's in radians and not in degrees. If you've got a different calculator, you'll have to ask me so I can look to see how to switch the mode of your calculator. But with the Casio, hit mode twice, mode, mode, number 2, so that you're in radians. So, first of all, we're going to look and say the cosine of theta is equal to 0.5974. That's a positive number. We know we're going to get 2 answers, and so we have to think about where cosine is positive. So, cosine is positive when my x value is positive. So I'd have to be in quadrant 1 or quadrant 4 in order for my cosine to be positive. So first thing I'm going to do is just put that into my calculator, but I want to do the inverse cosine of my 0.5974. On the Casio, you don't really need the parentheses. I believe if you have a Texas Instrument, it will put the parentheses there. So either way should work. If you're on the Casio, on the Texas Instrument, you need the parentheses. So you're going to hit shift cosine to get inverse cosine. 0.5974 and hit equals. And I get 0.93054. We're rounding our answer to the nearest hundredth, so 0.93. 0.93 would be my answer for quadrant 1. I also want to find my answer for quadrant 4. So to find quadrant 4, I would have to take 2 pi minus 0.93. So for 2 pi, you could take 3.14 times 2 and just use 6.28. Or on your calculator, you can do shift and the pi, shift. First of all, I'll hit the 2, shift and the pi key and use 2 pi that way. I'm just going to use the 6.28. So 6.28 minus 0.93 going to give me 5.35. And so that's going to be my other answer. So 0.93 and 5.35 would be the two that would have a cosine somewhat equal to 0.5974. Number 8, again we're going to use our calculator. We're doing 4 tangent of x equals 5. We want to solve that. So we want to do the tangent of x equals 5 fourths. So again, we're going to do the inverse tangent of our 5 fourths. Again, sometimes you need the parentheses, sometimes you don't. With fractions, I usually put the parentheses around there just to be on the safe side. We want to think about the tangent. Tangent would either be a positive over a positive, which would be in quadrant 1, or a negative over a negative, so in quadrant 3, for my tangent to be positive. So, inverse tangent of 5 fourths, if I use my calculator, shift, tangent, in parentheses, I'm going to put 5 fraction 4. I could do 5 divided by 4. If I hit equal, I get 0.8960. I want to round to the nearest hundredth, so my 89 is going to round off to 90. 0.90. That's my answer for quadrant 1. If I want to do quadrant 3, I have to take 180, or 3.14, which is pi, plus my 90. So 3.14 plus my 0.90 gives me 4.04. Those would be my two angles. That would give me approximately 5 fourths for my tangent. The last one, we have the sine of theta equals 0.492. Again, we're going to do the inverse sine out on our calculator. For my sine, I want my y value to be positive, so in quadrant 1 and quadrant 2 is where my sine is positive. And so first of all, if I do my inverse sine, so shift sine of 0.492, I get 0.5143, rounding that off to the nearest hundredth. 0.51 would be to the nearest hundredth. Since I'm going to be in quadrant 2, I would have to take pi, or 3.14, minus my angle. So 3.14 minus 0.51. 3.14 minus my 0.51 gives me 2.63. So, always keep in mind you should have two answers. You have to figure out, since all of these were positive, where your sine, cosine, and tangent is positive, or it might be negative, so you'd have to figure out where your sine, cosine, or tangent would be negative. Also make sure then that on your calculator you might want to change it back to degree mode right away instead of leaving it in radian mode. To switch it back to degree mode, you just hit mode, mode, and put 1, and then your calculator's back in degree mode. You'll see there's a little D up there instead of the R up there, so you know your calculator's in the right mode. (10, 11, and 12), we're solving a basic trigonometric equation. This time it doesn't give you the parameters that you have to be between 0 and 2 pi. So they're going to have answers that look like this. X equals 2 pi over 5 plus k pi. K is an element of z, which is the integers. That would mean that every 180 degrees. So 1 times pi would be 180, 2 times pi would be 360, and so forth. Now that's normally what you use for tangent and cotangent. Occasionally we have it on the sine or the cosine, but most of the time tangent or cotangent. Sine and cosine's period is usually 2 pi, so it'll look like this. 8 pi over 7 plus 2k pi, with k being an element of z. So first thing we want to do is solve our equation just like we did before. So we're going to subtract our 1 and say, okay, the cosine of x is equal to 0. We're then going to go back on our table that we used before. And I didn't flash that up there. It's going to erase my board, but I can rewrite that. But you want this table again where you can look up your sine, cosines, and tangents. So since it was 0, we have pi over 2 was cosine, yeah. Cosine pi over 2 and 3 pi over 2. So if I go back here, normally we would have said, okay, cosine of x equals 0 at pi over 2 and at 3 pi over 2. But notice those are exactly 180 degrees apart. Pi over 2 is 90, 3 pi over 2 is 270. So instead of writing two separate answers, we can combine this into one answer, starting with our pi over 2 plus k pi. I'm going to go 180. So if I add 180 to this, I'd be at 3 pi over 2, and then I just keep going half a circle, half a circle, half a circle, half a circle. K being an element of z, that means I'm going to take it times 1, times 2, times 3, times 4, and it's just going to go on and on forever. Normally, you have two answers, but because these two angles were exactly 180 degrees apart, we can combine it into one answer instead of putting in two separate answers. Let's look at the next one. It says the sine of theta minus 1 equals 0. So I'm going to add 1 and look up where the sine of theta is equal to 1. So looking at my chart, sine equals to 1 is pi over 2. And that's the only one I see. So we just have that one answer, pi over 2. Now on this one, since my period is 2 pi, it's going to be at pi over 2, and I'm just going to keep going around my circle. This one I'm going to use 2k pi. And k has to be an element of z. So we only had one place on our circle, and to get around our circle every time we have to go 2 pi, 2 pi, 2 pi, 2 pi. So our answer looks like that. Normally we'll have two answers that look like that, but we only had one that was equal to sine of theta equals 1. If we look at the third one here, the third one's probably going to look closer to our answers normally. If I solve this, I'm going to add my square root of 3. So cosine of x is going to equal square root of 3 divided by our 2, since we have to divide by the 2 to solve that. So if I look up on my table, where is the cosine of x equals the square root of 3 over 2? We have at pi over 6, and then we have 11 pi over 6. So on this one, we're going to get two separate answers. Again, with sine and cosine, our normal period is 2 pi. So we're going to add 2k pi to both of those. And of course, k is going to be an element of z. These will be choices over at the sides that you'll have to click on. You won't have to type that, but you will join these with the word or, because I'm going to get two answers on this. Because pi over 6 and 11 pi over 6 are not 180 degrees apart or something that's divisible evenly, I have to do them two separately. So pi over 6 going around my circle a whole bunch of times, 11 pi over 6 going around my circle a whole bunch of times. So normally, again, for sine and cosine, you're going to add the 2k pi because you're just going to keep going around the circle once, twice, 3 times, 4 times. Occasionally you can combine them if these are 180 degrees apart, or even if they're 90 apart, I can take pi and divide it by 2 and do 90, 90, 90, 90. But most of the time, our period is 2 pi, and so we're going to have that 2k pi on the end. (13, 14, and 15), solving a basic trigonometric equation involving tangent, cotangent, secant, or cosecant. So again, doing the same things we did on 10, 11, and 12. This time we're working with tangent, cotangent, secant, and cosecant, but solving our equation. So I'm going to subtract my 1. tangent of x equals -1. I'm going to go back to my chart, which again I forgot to show you since we're on the same page, but in case you happen to look later at the thing, we need this chart where we can look up our tangent, cotangent, secant, and cosecant values. And so going back over here, we said tangent of x equals -1. So if I look that up in my chart, after I find my chart again here in my pile, tangent equal to -1 would be at 3 pi over 4 and 7 pi over 4. Now notice that those are again 180 degrees apart from each other. 3 pi over 4 is 135 degrees, 7 pi over 4 is 315 degrees, but on tangent and cotangent, that's pretty much always going to happen, is that these are 180 degrees apart because its period is only pi and not 2 pi. So these ones we're going to be able to combine into just the one answer, like the very first problem on the previous ones. And so in this one, we're just going to say 3 pi over 4 plus, and we're just going to use k pi instead of 2k pi and have to do two answers. And, of course, k is going to be an element of z. K is an integer, in other words, 1, 2, 3, 4. On the next one, if we solve that one, first of all, we're going to add our 1. And so we're going to have the square root of 3 cotangent of theta equals 1. We're going to divide that by the square root of 3. We have to rationalize our denominator. And so we get square root of 3 over 3. So we're looking for where the cotangent of theta is equal to square root of 3 over 3. I've got to find my table again. Keep losing it. Cotangent. Last column, square root of 3 over 3 is at pi over 3 and 4 pi over 3. So again, you can see that those two angles are 180 degrees apart, or just pi apart. And so I'm going to combine that into 1 using my first angle. I'm starting at pi over 3. I can go k pi, add 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, with k being an element of z. So almost always on tangent and cotangent, I'm going to have plus k pi instead of 2k pi, and I'm going to combine my two answers into 1. And number 15, this time we're doing a secant. Secant's normal period is 2 pi, just like sine and cosine. And so solving this, whoops, board wants to be difficult. We're going to have square root of 3 secant of x equals a positive 2. And so secant of x is going to equal 2 over the square root of 3. If I rationalize my denominator, secant of x is going to equal 2 square root of 3 over 3. And so if I look up my secant, under my secant column, 2 square root of 3 over 3 is at pi over 6. And then if I look for another 2 square root of 3 over 3, I am at 11 pi over 6. Again, these are not 180 degrees apart, so I'm going to have to use the 2k pi and put in two separate answers. So I'm going to have pi over 6 plus 2k pi, with k being an element of z, or 11 pi over 6 plus my 2k pi, with k being an element of z. So when those angles are not 180 degrees apart from each other, I'm going to use two answers with a period of 2 pi in order to get them all in there. 16, 17, and 18, we're finding solutions when they're in factored form. And these ones will be all set equal to 0. So I can either say this equals 0 or this equals 0 and solve them. Again, these ones we're going to stick between 0 and 2 pi, so we won't have to put that weird stuff at the end. And so we're just basically going to solve each of these separately. Starting here, I have the sine of theta equals 0 then. So sine of theta equals 0. So I'm just going to go ahead, look at my table, find my table again. Under my sine, I'm equal at 0 and at pi. You'll also see that it's equal at 2 pi, but we're not including 2 pi in our answer. So 0 and pi. Over here, we would say 2 cosine of theta minus the square root of 3 equals 0. So 2 cosine of theta equals a positive square root of 3. We would divide by 2. So cosine of theta would equal square root of 3. Let me erase that. Square root of 3 over 2. So again, I'm just going to look up in my table. Under my cosine, square root of 3 over 2, I have pi over 6. Cosine of theta equals square root of 3 over 2 is at 11 pi over 6. All 4 of my answers are different, so I'm going to put them all 4 in. 0, pi, pi over 6, and 11 pi over 6. And all 4 of those would go in for my answer. If you happen to have one that repeats, you don't need to put it on your list more than once. And so I did them both separately, and then I just listed all of my answers. So on this one, if my cosecant of x is let me try that again. If my cosecant of x minus the square root of 2 equals 0, then my cosecant of x would equal positive square root of 2. So I'm going to look under my cosecant equals square root of 2 at pi over 4 and 3 pi over 4. So I did that one there. I'm then going to go on the other one. It says 2 sine of x minus the square root of 3 would equal 0. So 2 sine of x would equal positive square root of 3. So sine of x would equal square root of 3 over 2. So again, I'm going to go back to my table, look under my sine for square root of 3 over 2. I'm at pi over 3. And square root of 3 over 2 under my sine column, looking at this really tiny one and it's hard to read, is at 2 pi over 3. So again, all 4 of my answers are different answers. I'm going to just list all 4 of them. So pi over 4, 3 pi over 4, pi over 3, and 2 pi over 3 are all of the answers that would make that true. Number 18, same kind of thing. Let me move my board here as far up as it will let me go, which is that far. So again, I'm going to just break these down into 2 problems. 2 cosine of x minus the square root of 2 could equal 0. So 2 cosine of x would equal square root of 2. Divide that by 2. Cosine of x equals square root of 2 over 2. So looking at my table, cosine equal to square root of 2 over 2 would be pi over 4. And if I keep looking for square root of 2 over 2 under my cosine, 7 pi over 4. Solving my other one. I have 2 sine of x minus the square root of 2 equals 0. So 2 sine of x would equal positive square root of 2. So sine of x equals the square root of 2 over 2. If I look under my sine for square root of 2 over 2, I'm at pi over 4, and I'm at 3 pi over 4. Now you'll notice on this one I have pi over 4 in both of my answers. I don't want it on my answer twice, so I'm just going to say that I have pi over 4, 7 pi over 4, and add my 3 pi over 4, and just put in 3 answers instead of putting in the pi over 4 twice. So if something repeats, only want it in my answer once.